Okay, good morning, everyone. Okay, so I think most of you are my previous calculus students, so we meet again. So let me check. Okay, so we are now in a course entitled the Engineering of Mathematics. So I will introduce you to our syllabus first, how the evaluation and the textbook that I'm going to use. But before that, yeah, I think if you are just taking my course now, this is my email. This is the fastest way to reach me. Yeah, I think you can just take a photo or just write the notes. So yeah, the fastest way. If you want to ask something or maybe need something of me, so you can write at my email. Okay. Okay, and then this is the textbook. Okay. Textbook, the Advanced Engineering Mathematics by Dennis Zill. This is the 7th edition, but it's okay if you have the previous one, the 6th, the 5th. They are fundamentally the same, so you can just use that one as well. And then the prerequisite for this course, for single and multivariable calculus, students are expected to know. Okay? So if you are not knowing that part, then that's your problem. Okay. I tried my best in between of the section or chapters. If there's something related to calculus, I tried my best to review, but I think we are not having much time if you are reviewing all the calculus part. Okay. So I'm saying this from now. If you are in the middle of the course and you feel that, oh, this part, why the professor didn't told us the explanation, blah blah blah, because the explanation probably is about calculus 1 or 2. Okay, okay, so I'm just saying this now, so you need to prepare. Okay. Other references. If you have another textbook that's also, I think, good, the Krasik is also advanced engineering mathematics. They have a similar chapters and similar narrations, but different. I think some parts are having a different, probably have additional information, and the other one maybe they have another information as well. And also these two websites, which is the Wolfram Alpha and the GeoGebra, which I think I'm suggesting to check this out. I think if you're taking my calculus before, I already said these two are expected to know. So I don't know if you are already explored this part. This is quite good. Wolfram Alpha is the computational database that you can ask mostly everything. So I think now, as in processing system, I think ChatGPT better than Wolfram Alpha. But they have the Wolfram Alpha plugins if you are paying subscription to ChatGPT, so you can work out all mathematical problems in ChatGPT with correct result. GeoGebra, this is for a graph. So if you want to visualize your graph, you have a function and you want to know how to graph it, I think GeoGebra is one way. Of course, if you are familiar with other software such as the MATLAB or any other software, that will be really good as well. I think they are performing better because GeoGebra does the basic functions very well. But if it's going to be more analytical, like if you need for more references in the future for collecting raw data, I think MATLAB that will be, I think, much better. So that's some references and some notes that you need to prepare. Okay. All right. I think we can move on to the evaluation part. Okay. So I'm just saying this from now. This is the percentage because by the end of the day, you get the final grade, and then students complain, blah blah blah. But here it is. Okay. This 10% and 5% seems small, but this is if you are having like problem in the decimals in your final grade. This will be it will be significant to make it going up. Okay. So make sure that you get this 10 and 5%. Okay. Quiz 25. Yeah, 25, 30, 30. Okay. There's no TA, so the TA percentage goes to the midterm. So quiz, expectedly, we are going to have at least 3. But if we want more, we can have 4. The quiz main idea is to help you get the score. Okay, so that is the idea for the quiz. For midterm and finals, that will be your real exams. So the quiz can be held offline, like in class, or online if we don't have time. So we can have an online, and usually for online, I'm quite flexible. So you can have your own notes, your own books, and prepare the quiz. But as I mentioned before, I think since the calculus class, please do it by yourself. You can discuss beforehand, but don't do it like in a group. Okay? And if you're just copy paste your friend's notes or friend's answers before the quiz, well, you can have a good score, but the chances that you are learning and preparing for the other exams will be very low. Okay? So final 30%. The participation, this will include all the, usually I will have, like in calculus class, I will have a post test, but not in every class. So maybe in a week, maybe just one time. But sometimes there will be 2 times, like because we have 2 classes, right? But usually we will have only one post test. Okay, that's the evaluation part. Any question here? Any question here? And I already recorded, so you have complaint later on. Refer to this video. Okay. This is a little bit what we are going to cover in the lecture, and hopefully this will be helpful in the future. Okay. The first part, this is all about differential equations. So the first order, second order, higher order, we are going to try to cover. Although probably much of our discussion is this first 2, the first order and the second order. The higher order, because it's quite complicated, maybe just several techniques that we are going to discuss. Okay. So usually after the first part finished, this will be the midterm. So we finish the first part, midterm, and then second part, final exam. So in between there will be quizzes. Okay. So either 2 here, or maybe 1, and then another one is the online quiz, and then another one here. So 3, or 2, and that can be also happen. And for the second part, there will be a Laplace transformation. Anyone familiar with this? Not yet, right? This is actually still differential equation, but with some unique tools that we call the Laplace transform. Linear algebra, it's include matrix, vectors, determinants, and linear system. Okay. This is basically solving the linear equations, but using matrix and using several techniques. Okay. And linear algebra, if you are considering yourself to want to go discuss more in programming or coding, that's usually the first step you are going to learn, because this is the very first step for the logic behind the programming. And then the last part is the eigenvalue problem. This is actually matrix, but we have this eigenvalue. Actually, this has some subtopics from this part, but I didn't write all, but just mentioning eigenvalue. Okay. Usually we are having another part, which is the surface integral and line integral, but that will be supplementary. Okay, I don't think we have time to cover all that much information in one semester. So I hope it will be covered in the engineering mathematics 2, because we are in engineering mathematics 1. Okay, any questions first? No? Okay. So I think the last slide for the introduction is you need to have a basic foundation in calculus. That is very important in this class. So who failed calculus? Calculus 1. Calculus 1. 1. 1, 2. How about the calculus 2? Calculus 2, who didn't take calculus 2? Also, I will consider not yet taken as a fail first. Okay, 1, 2, 2, okay. Okay, so if you want to pass this course, you have double workload. So calculus plus another one here. Okay, but actually, since this is the first part in our course, that will be about differential equations. That is actually in calculus 1. So I think we can go for we can go for our notes here. Okay. So what we are covered, the first step is the ordinary differential equations. So let me write here, differential equation, I think too thick. Okay, let's say we are having our functions, let's say f of x. Let's say y equal f of x. So we define y as a function of x. Okay, let's start from the basic. What's the implications when I'm writing y equal function of x? Of course, you understand what the function is, right? The function is like a system. So you put something inside, and it will have some process, and then it will have some output, which is this y is the output, right? Or the f of x. Something that you put inside is x. So we call x as independent variable. Okay? And we call y as a dependent because it depends on x. Okay? So we call this independent variable. This is dependent. And then we know that from calculus 1 that we can have this term y prime. Or if you want to write f prime x like that, which means that this is the first derivative okay, the first derivative. Or sometimes we are taking the derivative as d dx, or in here we can write dy over dx, which is equal to f prime x, or we can just still writing that y prime. Okay, so what's the differential equations? So it means this is our derivative, right? The first derivative. It means the equation, okay, that has differentials inside, which means I can write like equations like this. For example, y prime plus 2y plus 6 equals 0. This is we call a differential equation. Okay. And to solve our equation, we need to make this into this. We need to find what is y. And that will be the solution. And sometimes the solution is not only like a single solution, perhaps it has a family of solutions, because remember, if you have a derivative like this, and you want to make it into the original one here, you need to integrate, right? When you integrate, you plus something, right? You plus a constant, because the constant, if you derive, it will be 0. So you have like plus c, and plus c can be any numbers, which means that the solution can be infinite solutions, right? Okay, so what we are going to do within this chapter, differential equation, we are going to have like how many techniques that we can do for solutions in differential equation. And before we going through these techniques, we need to categorize first what kind of differential equation we are going to overcome. Okay, just perhaps I'll review a little bit. A little bit review here. Okay, let's start from the simple one, integral of 1 over x dx. What is this? Okay, 1 over x integral?
ln.
Yeah, ln. And then? This one? Anyone agree? All agree? Do you agree? Do you agree? Agree? Do you agree? 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 Is there something miss or? Yes, yes, yes. Okay, no. Okay. This is small stuff, but it's actually significant. Okay. So don't forget this. Okay.
Okay.
Yeah, the absolute value. Okay. How about the sine inverse? It's not memorization. If you forget, you need to find how to get this. Don't memorize formula blindly. Okay, do not blindly memorize them. It's good. Sometimes it's good, but it's. I think it's better if you understand the scratch, how to get it from the scratch. I don't know. So the idea is, let me write here. You can get the idea from this triangle. Let's say this is theta, okay? And if because if we take the inverse of some trigonometric expression, it means that this is the angle, right? Okay, got it? So we are taking some angle that is the sine inverse of x, okay? So x is, right? So we can try to make it into our triangle, which is x here, agree? And 1 here. And what about this one? This one will be square root of 1 minus x squared. Okay. Now, we need to have good calculus here. So we differentiate because we want to know what is the derivative of that. Wait. This is supposed to be, sorry, not integral. It's supposed to be the derivative. Sorry about that. That's why some of you are confused, right? Okay, sorry. Should be this. Why I'm writing integral? Sorry. I should be preparing integral and derivative. Should be derivative. Okay, sorry. But this is taking the derivatives and getting that this will be cos theta. But since theta is the function of x, we take the implicit differentiation, right? So we take the theta dx. Or if you want to write directly that this is y, and you get the final answer, this is also okay. I'm just making angle to make sure that you understand the inverse is the angle. Okay. So we get that d theta over dx is 1 over cosine theta, which is from our triangle here, perfectly this. So the whole point here, this dy dx, if we take y as a sine inverse, this will be 1 over. So you can write down here that is 1 square root of 1 minus x squared. Okay. And remember, why this theta need to be having this form? This is because it is dependent. Okay, dependent variable. This is independent. That's why, because we are deriving with this independent variable, we can directly just write this one. And this one is cosine, right? But we need to write the derivatives of this theta, which is d theta over dx, because it's dependent variable. It's called the implicit differentiation. Implicit. We derive implicitly. And later in our engineering of math, we are going to have explicit solutions, implicit solution, which is actually not much different from our understanding of this implicit. Okay. Okay, just a small review, and sorry that this is derivative, not integral. Maybe the previous, before you feel confused. Sorry about that. But what's happened if this is integral? Can you do that? I think you can use the integration by parts, right? But I think it will be a little bit long. Okay. This is just a review, okay? Just a review. So this is in early beginning of the semester. Let me just put a sticker here. This is review. Okay. The sticker you can find in the line. I'm the one who made it. Okay, so you want to take notes here? Okay, if not, you can look your calculus notes. Oh, calculus 1, right? Okay. Okay, let's move on to the type or classifications. So let me rephrase what's the differential equations. Okay. So equations contains the derivatives contains the derivatives of one or more dependent variables with respect to one or more independent variables. So it can be not only x. That's where the partial will be defined. I hope my writing can be. So equation contains the derivatives of one or more dependent variables with respect to one or more independent variables. This is variables. My handwriting is not really good. Let me write nicely here. Which you can see from this one here, several examples on how we can write some of the differential equations. We can write this like something like this. So we can have this first derivative, and then y, and then x, okay? Function of x. Or we can write the second order. This is what we call the second order. It means the order means how much you derive. Okay? This is the first one, you derive only one. Okay? This is you derive twice. Okay? The second order, dy dx minus 12y equals 0. Also differential equations. And we can have more than one dependent. Okay? We can have dx dt, dy dt. Okay? Or we can have this. We can have two independent variables, okay? Which is, I think you learned before in partial derivatives, right? But in our course, we are going to focus on the ordinary differential equation, which is this one. So we are not really going to talk much in partial, because this is already a lot of content. So we call this one is the ODE, which means ordinary differential equations. So here, it's ordinary. Let me. So ordinary differential. We write differential as diff and equation as EQ. And this one is the PDE, the partial differential equation. Okay, and how to write? Sometimes you write like this, or you can write with the more simplified versions, like y prime plus 6y equal e to the negative x. Or maybe the second one here, you can write y double prime plus y prime minus 12y equals 0. Okay, you can write as simple as it is, or you can write like this. It's okay. Sometimes it's too much. I think better to write with this accent like this. It's simplified your writings. So we have two classification in general for differential equations. And then we can also take a look, as I mentioned, we have different order. So let me go put high here. So for example, if we have this kind of equations here. So we have this is the second order. And be careful. Sometimes when you deal with this differential equation, you are having an error and make this 3 as your order. This is not an order. This is the cube, not the derivative. Okay? Be careful with that. So what is the highest order here is the second. So we call this is the second order differential equation. Okay? This one here, the highest order are this 4. We call this 4 as the highest order. The fourth order of differential equation. Usually we focus more on the first order and the second order, and above than that we call the highest order, the highest, higher order, okay, the higher order. And sometimes we have something like you are given with these equations, y, so this is example, y minus x plus 4x dy dx equals 0. Or maybe let me write more complex. Okay. This is still the same equation, but I will write from this part plus 4x dy. So this is also differential equations. The first thing you need to do is to make this as dy over dx. Because we see that we have dx, we have dy, so we need to normalize this as our differentials. So how to do that? We just divide by dx, right? So we are going to divide by or multiply with 1 over dx, which resulting in y minus x plus 4x dy dx equals 0. Or we can write 4x dy dx plus y equal x. So usually we keep all the dependent on the y on the left side, and the other part like a constant, or even the independent on the other side. Sometimes this is, I think, better for analyzing the differential equation. Okay? Or we can say the general form. So general form for this differential equation, we can write, let me write with f, big F like that, x, y, y prime, y double prime, dot, 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 y with order n is equal 0. So this is the general form. And we can also write what we call the normal form. What's the difference? The difference for normal form is it's directly describe the differential. So we can write as d and y dx n, which means n is the order, okay? And we can write as a function of x, y prime, and dot dot dot, y n minus 1. Y n minus 1, because it's actually symbolizing that this n is actually derived from here. Okay? So we need to minus 1. Okay? So if n is 1, okay, so if n is 1, so n equal 1 means that dy dx is f x y. Okay, and if n equal 2, it means that x, y, and y prime. Okay. So this is what we call classification by the order. The first, second, third, fourth. I think I can write something here to mention that this is classification by order. So this is classification. Put sticker. Okay. Okay, so next is the classification by linearity, because the linearity will be important because there will be some techniques that specifically directed to this linear functions. Okay, so this is what we have before. So this is general form. This is normal form. But before we go to the linearity, I don't think this is a good example. I think we can go directly to classification by linearity. Let me go through from here. Okay. Okay, just focus on the red equations. Okay. So before, for the order, we can see the order within this dependent variable, right? Y dy dx, and then this dn minus 1y, dny, okay? All that dependent variable. Now for linearity, we're going to focus on this coefficient for the a. So if we see from the pattern, this n, both independent and dependent variable, they have the same n. Okay? So if we take n equal 1, for example, if we take n equal 1, we have a1x and then dy dx, and then plus a0 x and then y, and equal g of x. And if we take n equal 2, equal g of x. So we call this is the linear, this is the linear first order. We call this is the linear second order. So first, how to check the linearity? Okay. So first, I said that before on the coefficient. The dependent variable also important. So how to check linearity? So linear characteristic. There are two. So the first one, dependent variable y and its derivative are of the first degree. What's the meaning the first degree? It's the power, okay? Not the differential equation as in order, but the power itself. Like squared, cubes, okay? So each, or the power of each term involve y is 1. Okay. So let me write first here the power. Okay. The meaning of power is the exponent. Okay, the exponent, the exponential. Okay. And second, the coefficient depend at most on independent variable x. So as long as the linear characteristic can be achieved, then it is a linear. For example, if you see, like, we have dy dx, we know that this is the first order, but if we take squared like that, it's a first order but non-linear. Okay. Or we have a function that is already non-linear. For example, like a trigonometric function, like sine, cosine. For example, if we take that sine y, for example, it's already non-linear. Okay. So this is non-linear. Or even like e or logarithmic, this is also non-linear. Let me write some example here for some equations. We are not yet finding solutions, just to set some definition first. Okay, we are going to have a break, and let's see if we can distinguish linear and nonlinear. Okay, we are going to have a break for a while. Continue. Let's start from this example. So I have 1, 2, 3. I ask which one is linear, which one is linear ODE, which one? The linear? Let me, okay. So remember, we have two characteristics. So first one is, we are going to see the dependent variable y and its derivative are the first degree, which means this degree is related to the power, okay, not the order. Okay. The second one, the coefficient depends at most on the independent variable x. So from these three examples, which one is linear one? Yeah, who said? Yeah, the first one. Agree on that? Okay, everyone agree? Do you agree?
I would agree.
Okay, okay. Okay, agree? Okay, you still feel not really convinced, means that we need to have some more examples later on. Okay, so the first one is linear. Okay, the first one is linear. So every x is not really, say, because it's independent, so we can say we are going to check the dependent first. So the dependent, is there anything wrong in the dependent? I think nothing's wrong with that, right? It's the third order, first order. This is the just normal dependent variable. And this is also x, right? Not y. So it's not non-linear. So it's linear. Okay. So it's linear. So let me write here. So it's linear. How about the second one? The second one. Is it linear?
No.
Yes, because we have this, right? So it's non-linear, right? So let me write here. This is so here this is power is above 1, so non-linear. So what about the third one? Non-linear, why? Because which part that makes non-linear? Just
I think the right part. No, the too wide. It makes it not linear. Yeah, I think.
the y is linear, right?
Yeah, is it?
Yeah, 2y is linear, but
Then the
yeah, yeah, of course. And the last this part. Okay, this makes non-linear. Why? Because not one, but because the coefficient should be depends on x. This is x, right? So it's okay. But this is y, right? So that makes it non-linear. Okay. Or if you want, we can multiply this. So y prime minus y prime. Y prime makes it non-linear. Okay. So we can say that this is coefficient depends on y, so non-linear. And for the linear one, later on we are going to see we have some special structure for the linear differential equation that we might have some techniques to find the solutions. Okay. Before the introduction, we are going to just describe what we are going to have, and I think next week we are going to go for the techniques. Okay. Okay, now I think before this solution, let me just go through just a blank paper. Or if you want to just write this if you haven't finished. Let me write. Or if you have any question first? Do you have any questions?
Well, we should know
Mm-hmm.
it is linear or non-linear.
Okay, the first one is you need to check the this differentials. Okay. If the differential like this one is already okay, we think it's linear, and then check the coefficient. Second one, check the coefficient. If the coefficient all is in x, I think it should be okay. Okay. For example, if we have like this, or if I change, for example, if I change that we have the another terms like maybe here, maybe change this to y like that. Is it still linear? It's not. Now it's non-linear because we have this by the definitions, the exponent is nonlinear, and it's already in white here, so it's nonlinear. Okay. So let me put back to the original form. Okay. So if you take this and then make squared, it becomes nonlinear. Okay. If you see any dependent variable that by nature is nonlinear, it's nonlinear. Like e to the y or trigonometric sine, cosine, that's nonlinear. Okay. Or the second part is the coefficient. If the coefficient is y, then it makes it nonlinear as well. Okay. So remember, to make it linear, you make sure the order, not the order, the power is the first degree, which means this one here, there's no other power, right? The second one, the coefficient should be in x, okay? Should be in the independent variable, or I say x. Actually, variable can be any letters, right? But it should be independent variable. If this is y cubed, then it makes nonlinear. Okay? Okay, I hope you get it. So only two factors. The dependent here, or this derivative, need to be the first degree, and the coefficient need to be in x. Okay? Just two. Okay, the next one is I would like to talk a little bit on a solution. So before we go to details, so solution, for example, if we take dy dx is 0.2 xy. What will be your solutions to offer? Perhaps, if we make it into for example, if we take, I think that will be the techniques. Let me just give you this solution first, okay, and then we're going to. So if we take y equal e 0.1 x squared, okay. If we take derivative of this, okay, so we take the derivatives, we get that this is calculus review again. So dy over dx, and then the e will be, it's still e, right? And then we need to multiply with the chain rule, right? So we need to multiply with 2 0.1 x, or since this part is our y, so I'll write this y. So we have dy over dx is 0.2 xy, right? Okay. And you need to keep in mind, okay, because the e exponent, if we derive or if we integrate, this exponent will appear again and again and again, right? So it's best to think that this is kind of multifunctions, okay? I mean, for our solution. So it can be a solution for many problems in engineering of math in our course, okay? Because it's really, you can utilize, I think, in most cases, and it will be very important. Okay? But from what we have here, what we have proven here, that it's true that this is one of the solutions that can be for our differential equations, okay, right? But what's the problem here is the interval. Is it going to be verified for all intervals? Some solution maybe only for some specific interval. So we can say this solution, okay, so let me write here. So y equal e is a solution of dy over dx equals 0.2 xy on interval, for all interval, okay. So let me write here the solution for ordinary differential equation. So any function, let's write a function, let's say psi, defined on interval and possess at least and derivatives that are continuous on I, it means that when substituted, it means if we check the solution, okay, if we check the solution into the nth ODE, reduce the equation to an identity, which means it can be solved. Okay. So we say that it is the solution of the ODE on the interval I. It means that we can think this solution, for example, this one here, we can think that if we think that this is solution, we can, right here, we can try substitute. We can try substitute on the left, which means we are going to take this as like that, and make it into identity, which means it become itself, okay? Or we can substitute the right side. Yes?
How is the word on the red line?
Red line. Red. Huh? Oh, N TH. I mean, it can be first, second, and order. Okay. Because the ODE can be first degree, can be first order, can be second order. Maybe it's my writing. Let me. Okay. which means that you can propose a solution from a simple derivative and integrations. If you know how to make that, you can propose a solution, perhaps trial and error, and then verify the solutions. And if it's satisfying, then it will be the solution of our ordinary differential equation. But it means that it's just trial and error, not really sophisticated techniques. Okay, and if we get more example for, let's say we have y double prime plus 2y prime plus y equals 0. And let me give you some proposals for the solutions. Let's say we take the y equal x e to the x. And we can try to verify. Okay, so verify. So we take the y equal x with e whole power of x, and we try to take this first derivative. So anyone still remember how to write this? We have x e to the x. Okay. Again, a little bit review of calculus. Mm-hmm. Yes. You will have two different parts, right? Something plus something. Agree? Okay. So this is what we call the product rule, right? The product rule. Sometimes I forgot the terms, but I know how to derive it. Yeah, product rule, right? Okay. So we have, this is one function, this is the second function. So we are going to have this method like this, right? So y prime is f prime g plus g prime f, right? So we are going to have e to the x plus x e to the x. Agree? Right? Okay. And then because we have the second order, we need also to check the second order. Okay. Later on, this kind of verifications, also we are still going to do that more and more. Because if we get from some techniques, we need also to check whether our solution are satisfied or not. And then check the double prime here. This will be e to the x. And this is again the same thing. So e to the x plus x e x. Or we can simply write x e x plus 2 e x. Okay. And then check whether y double prime plus 2y prime plus y, this will going to be equal to 0. I think this should be minus because it doesn't make sense. How can it be 0? It's plus plus, so it should be minus. Okay, it should be minus. Okay. But if it is plus, then you can say the solution doesn't satisfy the equation, the differential equation. Okay, you can check. We can multiply this by 2. Okay, and then we plus this. I think this will cancel. This will result in 2 minus 1, so 1. Or minus, right? Minus, and then minus plus is 0, right? Okay, or you can just check this, multiply by 2. Okay, and multiply by -2, and then you can take the plus. So x minus 2x is minus, and then plus is 0, and then the other one is e, minus 2e plus 2 is 0. So it's going to be this, right? So it's also satisfied. So the y equal x ex satisfy Okay, now the question is it the only solution? Can we prove something that can be useful for the future? What other solution that might be? The other solutions, which usually we call trivial solutions, is when, for example, if we take y equals 0, if we try to put out in our solution in our equation, it's also possible, right? So sometimes we call this as our trivial solutions. So this is a trivial solution. So each ODE or differential equations possess constant solution y equals 0 that will be defined on the interval for all interval. Should be defined on the interval. So we call this a trivial solution. Okay, again, we haven't yet going through how to find the solution yet. This is just to verify the solution. Okay, now trivial solution. Yeah, because if you think in especially for ordinary differential equation, y equals 0 can be possible, one of the possible solutions for all the differential equations. But it's not only solutions, and because it's not really have some meanings, because yeah, it's true that it's satisfied, but it's not really what we wanted. So we call it trivial solution. It's only trivial, so not really meaningful. later we are going to have, there will be some specific terms in solutions, particular solution, blah, 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 and that will be the meaningful one, okay? The one that we want to find. Because if we just write, okay, the solution is y equals 0, but y equals 0 is for every differential equation. It's not meant for some specific differential equation. So that's why it's just trivial. We can just say that it's not really meaningful. Okay, this one is not really meaningful. Okay, the next one is what we call the solution curve. Okay, so the solution itself, okay, this is what we had before. So the solution can be described as a curve. And just for some graphs, okay, just to see the difference between when this is called a function and when this is called a solution. Okay, consider the y equal 1 over x. Okay, the first graph, the top one, is a function y equal 1 over x. Okay, of course, if we graph, we have the one on the bottom left and the one on the above part, right? And we see that there will be discontinuity on x equal 0. So the curve will not crossing this the x equals 0, right? Or we can say that the domain will be x is not equal to 0. Okay, that's as a function. But as a solution, for example here, for some specific case, we can say solution is only this 1 over x that is greater than 0. And that is the solution. So if we consider the differential equations, let's say x y prime plus y equals 0. So if we want to, and then we want to verify this as our solution. So we can take that and we try to differentiate this. How to differentiate? I think it's easy, right? So we can think this as -1. So we take differentials and we take minus to the front, so this will be going to the front, right? And x, and then we add more -1 on the power, so it's going to be -2. Or we can say this is like that, okay? So we can write this as -1 over x squared. So we want to verify this as we previously tried. So we try to substitute, okay? We try to substitute. So x, and then -1, and then plus 1 over x equal to 0. And it's satisfied, right? It's satisfied. It's back to the, or we can say it's the identity. So we could say that y equal 1 over x satisfy this differential equation. And the solution, okay, the whole solution, so on interval not containing 0. So this is the solutions, one of the solutions. Okay. Or solution can also is 1 over x, but we can take that as this. So this we call the solution curve. So which one to take, it also depends on the case. Sometimes you will given some specific value, For example, the value is on this region. So you will take this interval. If the value is on here, then you take this interval. Okay. Okay. Because it doesn't say in the specific value. We call the specific value as the initial value problem. Later we are going to see that. Because it doesn't mention that, so we can say it can be this or this. If you want to make the graph for that one, that's also fine. Another one, but you need to make it one by one. We cannot take two sides of this one as a solution. Okay. Any questions? Any question first? So that's how you take the differences between functions and solution. Function, you can draw all the things on the graphs, but for solution, you need to specify in which part. Okay? If we have like this continuity like this, in which part? This part or this part? Because there will be two different solutions, right? Okay. Okay, this y equal 1 over x also, we could say, in terms of solution, let me write here, is an, we can say, explicit solution of, what's the differential equations? X, y prime plus y equals 0. Or if you would like to take the previous example, the y equal x, ex is also an explicit solution of y double prime okay. And also the trivial solution, y equals 0, also explicit solution. So there will be explicit like this, and there will be also implicit. And I think the best way to explain this is through the examples. Okay? If you see the definition, it'll be a little bit complicated. Okay, now what is the implicit solution? Let me go through here for a while. If you read this, I think not really helpful. You have to have at least to draw an example. So what this is about is actually we are going to take a look on the differential equation itself. So for example, if you remember, okay, this is differential equation. This is coming from, let me take just to, so propose that we have this x squared. Let me just write a circle equations like this. Actually, any constant you have, if you take the implicit differentiation, it will be this, right? So let's take a look and have a review. ddx, okay. Okay, so what will be? So what's the result if we take the derivative for all these terms with respect to x and then plus
2y
dy dx? Okay, good. And then the constant is 0, right? And we simplify this and make this into, it's become negative, and then x and 2, this 2 is cancelling over y. Okay, agree? So we can say that this part, since we are using implicit differentiations, and why implicit? Because we are force out the y, we take derivative, just like with x, but because y is dependent variable with respect to x, then we need to add this one, right? So implicitly we are having some actually solutions. Okay? So we can say that this is an implicit solution. Okay? Because it's not in the form of y equals something, and then it like a functions, right? So we can say that the x squared plus y squared equal 25 or equal a constant is an implicit solution of dy dx Is it linear or non-linear? Linear or non-linear? Non-linear. Why? Not really true, because it's 1 over y. Remember, 1 over y is by nature is non-linear, right? Like this one. This is 1 over x. But here is 1 over y. So that's a problem. So it's non-linear. Okay? Just to make sure that we still have that connection with the previous sections. Okay?
So why is it not linear?
Because of the 1 over y. Remember, to check linearity, let me write here. Check linearity. First, check dependent variable. Second, make sure the coefficient is independent variable, or we can say x. So the dependent variable includes y, y prime, y double prime, and so on. So if the dependent variable by nature is nonlinear, then it's nonlinear. Like for example, it's already 1 over y. 1 over y is already nonlinear, right? Or if you change this 1 over y with sine y, it's also nonlinear. Or if you take y, make it squared, make it cubed, it's also nonlinear. Okay? This is not yet complete. Let me write the interval on interval, because we know it's a circle with radius 5, we can say we can make interval from -5 to 5 for the x. Now from here, we could simply have imaginations on what should be this x squared. Let me write here. The x squared plus y squared equal 25. We can write in terms of y equal function of x. For example, we can write as y squared is 25 minus x squared, which in turns, it has two different forms, positive and negative, right? Okay, now we call this two, this is explicit solutions. Okay? This one is implicit solution, which means the form is not in definition of y equal the equations, but it has, let's say, a complicated structure in the solution, and we call this the solution implicit. Okay? Or if we try to draw the graphs, then we might have the implicit solutions, the x squared plus y squared equal 25, this normal circle, and we can say explicit solution for the positive one, and then for the negative one, okay? With the same interval, Okay, I think I will end up until here. Okay. We don't have any post tests yet, but maybe next week, not this week. Okay. We'll just try to this week try to finish off just the introduction of the differential equation first. So any questions? Any questions? So you can say the explicit is if we take the equation of y. So y equals something, it's explicit. Okay, explicit. Okay. But if the y itself is in the equation, like for example like this one, then you can say this is implicit solution because it's not really in the final form. You can say that. Okay? The final form of the solution, usually we say y equals something that will be our final solution. But sometimes we could offer the implicit solution as well. Okay. Okay, I think that's the definitions. I think the best way to describe, okay, using the graph and how to write down the equation itself. Okay. Okay. Any other questions? Okay. So I think this will be the end of our lecture for today's class. So if you still have any question, or if you need the code, let me know. Just email me or chat me through Moodle. Okay. But the fastest way is through email, because the Moodle sometimes it has some delays. Okay. Okay.